Hello, everyone. Good morning, afternoon, or evening, and welcome to week 4 of the climate change course. This is a lesson on radiative forcing and forcing agents, so it's pretty straightforward, pretty brief, frankly. Do keep in mind that weeks 1 through 4, so including this week, really build into the second part or the second unit of the course, units or weeks 5, 6, 7, and 8. So it does all build on itself. So we'll begin. This is a bit of a review. We did address forcing before, but we're going to cover it in a little bit more detail in this lesson. So having said that, let's put this in presentation mode and talk about the main forcing agents, which would be these. So these molecules or greenhouse gases are forcing agents. Remember, these are the gases that can trap infrared energy in the atmosphere. The most important of which is, of course, CO2, at least in the context of present-day climate change discussions, water vapor, and methane, ozone and nitrous oxide to a lesser extent. Excuse me. All right, let's get going. So it's all about radiation, and the radiation being out of balance. That's basically climate change. If your radiation budget is out of balance, it is either in a negative or cooling mode, or in a positive or warming phase. So these are the two possible options if it's out of balance. Otherwise, you would remain basically or essentially around the same temperature all the time. So climate forcing agents, these are the agents, as I mentioned earlier, that can either cool or warm the temperature of the Earth as a whole when averaged as a globe. Radiative forcing agents, positive ones imply warming, negative forcing agents imply cooling. And again, do not think of positive or negative as good or bad. They just simply imply positive means you are adding. So you basically have a net warming taking place, and negative agents force cooling on the planetary system. Climate forcing agents can be natural and they can be anthropogenic. And again, this is a term you should know. Anthro, human, and progenic basically means caused. So anthropogenic means human cause as opposed to just simply natural. So natural forcings include the sun without any human, obviously, intervention. Changes in the parameter of the Earth revolving about the sun, and large or numerous volcanic eruptions, meaning you inject a lot of ash into the atmosphere. Anthropogenic forcings now include things like dark particles in the atmosphere, soot and dust from agriculture, soot from the burning of fuels, large-scale deforestation, changes in the use of land, large-scale increases in greenhouse gases due to these events, so industry and agriculture across the world. And the big forcing agents, frankly, these are the most important ones. I leave out H2O or water vapor because water vapor is something that we really have no control over. We don't increase the amount of water vapor. It's a fixed quantity. Carbon dioxide can be increased, methane can be increased, nitrous oxide, and CFCs all can be increased by human activities. Now, the distribution of water vapor can change, but that's different. Okay, again, these are the agents that human activities can directly affect since they rise and fall depending on the usage. Okay, so I hope you understand that basic difference and why water vapor isn't really in this list, or on this list rather. All right, so the solar constant, this is how much energy comes in through the top of the atmosphere. Every watt, every square meter, 340 watts per square meter. 102 of it is reflected. 238 of it basically is absorbed by the atmosphere and the surface. So if you add these two, you get 340. Now, if you absorb more energy, the Earth will warm. If you reflect more energy, so if you make this number larger, you'll be in the blue. If you make this less, it'll be in the red. So it's a really basic math equation when you get down to it. Right, climate forcing can lead to feedbacks. And remember, we talked about positive or negative feedbacks. And again, positive and negative doesn't mean bad or good. A positive feedback can lead to something like an intensification or reinforcing of the original forcing. This would be positive, or a weakening or counteract the original forcing. That would be a negative forcing. So you really need to be sort of in tune with that basic definition of what forcing agents and feedbacks are. So in terms of forcing, there have now been 3 really good reports dating back to 2005, AR4, 2011, AR5, and 2019, AR6. And we're comparing the forcing pre to the year 1750, which was basically largely believed to be the true beginning of the Industrial Revolution in Northwest Europe, what we refer to as the United Kingdom, Ireland, France, Germany, that region of the world, right? And these are the heat trapping effect of CO2 has risen. And basically it's been calculated in the 4th, the 5th, and the 6th reports. So think of it as an equivalent increase in sunlight, so more heat. So in AR4, that was an additional 1.66 watts per square meter to that 340. In AR5, it was 2.29. So it's up 43% from AR4. And in AR6, it is 2.72. So there you see the obvious sort of increase. Think of it as having a blanket in which you've stuffed more insulating material like feathers or foam or whatever the case might be. We have essentially made the atmosphere slightly thicker, so we have made its ability to retain heat more efficient. Make sense? Now, so the evolution of radiative forcing in graphic form. So we're going to look at the numbers. So we're going to look at these numbers, but we're going to look at them in graphic form. So here it is. So this would be 340. So this would be 341, right? Positive one. This would be 342. This would be 343. Get it? So here's that 2.72. 2.72. So this is for AR6. This is relative change in radiative forcing from 1750 to 2019. Notice some things actually contribute to a negative. So these are negative forcing agents. They help to cool the environment. Aerosols, land use. However, CO2, notice it contributes the most. So imagine if you add all these numbers, all these positives here, and then you subtract all the blue, what you get is this bar. Does that make sense? So you need to focus on the graphic here. So this is the 0 line. So if this red bar were basically exactly here, there wouldn't be an issue of climate change. Get it? We would be completely stable. But we are basically trapping more heat as a function of CO2, other well-mixed greenhouse gases, ozone, and so on. And then we are cooling the planet as a function of these aerosols and land use. So when you add all these positives and subtract these few negatives, this is what you get. And again, I'm sort of harping on it because it's a pretty significant graph to understand. Again, it says so right here, add all the values to the left of 0, to the right of 0, meaning negative numbers, and you get this. What the gray arrow is pointing to. Okay, so in summary, since 1750, in 1950, the increase was 0.57. In 1980, 1.26. In 2007, 1.6. In 2011, 2.29. And in 2019, 2.72. The trend should be clear. That's what we're focusing on. What's happening trend-wise. Again, it's all about radiation. So if you think about it in terms of a budget of carbon, in 1850, the concentration of carbon dioxide in the atmosphere was 280 parts per million. ppm, that's what that means. In 2020, the rate was 400 or greater than 400 parts per million. It's actually 417 as of the making of this particular video. So this is how much it has increased. So the sources are coal, oil, gas, cement, land use. There are things that actually bring it down, and we talked about carbon sinks. So you take these positive values and you subtract this, and you get this. Make sense? So these are the particular events or culprits of carbon addition to the atmosphere, and these are the ones that subtracted. And when you do the little math equation, you get this. All right. So again, if you add up all the numbers, all the positive and the negative forcings, the net anthropogenic number, again, 2.72. CO2 alone is responsible for 2.16 of this. So all the other factors contribute to the remaining 0.54. So CO2 is approximately equal to the net forcing taking place in the atmosphere. So CO2 by association is the main driver of climate and has been since 1750 in an ever-increasing fashion. And it will continue to be for the next few decades at the very least. All right, so again, being all about radiation. So imagine a graph. So this is the wavelength here, right? And water vapor in the blue, carbon dioxide in the red. And where they overlap, for example, here, they work together to be a very effective absorber of infrared energy. And this happens to be in the infrared window. So therefore, it is the energy that would be escaping from the Earth in the form of long wave radiation. And as a result, you get exceptionally good absorption of infrared energy. So you get a heating effect. In the visible range, what humans can see with your eyes, they don't absorb at all. So let's look at this. So here we have various elements, molecules, nitrous oxide, methane, molecular oxygen, water vapor, CO2. So nitrous oxide absorbs IR in two very specific wavelength. Notice this is absorption percentage, 0, 100%. So nitrous oxide is very, very specific in the two windows in which it can absorb IR energy. So it is not a particularly good greenhouse gas, even though it is one. It's not particularly good. Methane is a very strong absorber of IR energy. I need to fix that. It should be of, in two very specific wavelengths as well, in the infrared. Ozone, so O3, absorbs 100% ultraviolet. That's good, but infrared energy as well. That's bad. Water vapor absorbs IR over many wavelengths. Wherever you see the blue go to the very, very top, these spikes. And carbon dioxide absorbs IR at several wavelengths as well. Notice this whole range here, from here all the way to here, that is the infrared. This, the rainbow, is what we see, visible. Sunspots, they increase, there are increases in solar energy output, they correspond to increases in sunspots. So the more sunspots you have, the more active the sun is. And it has been observed to be a very cyclical event. Every 11 years, there's a peak. Every 11 years, very, very, very predictable. And we are headed towards a new peak in about the year 2025. Again, they peak every 11 years. It's one of the most predictable phenomena in nature. First observed a long, long time ago by Galileo. Here's an example of a less active sun in the year 2009 and the very active sun in the year 2000. So if we go back, the year 2000, right near the peak, the year 2009, near the bottom. 2009, weak. 2000, active. Right there. The carbon cycle. So carbon is often stored as fossil fuels in limestones. It takes a long time for that fossil fuel to generate and form, but burning it doesn't take very long. Production of cement. And think about it, carbon release in 100 years took millions of years to form and accumulate naturally. So that's why the rapid usage of such fuels has a significant impact on the climate system. That's the whole basic argument of climate change, as we talk about here in the 2020s. And here's what's happened. So globally, this is how much carbon has increased from the 1960s through 2020. Here's the idea of cement, gas, oil, and coal. They have all increased. And here's the breakdown by per person. So the United States is still the highest per person, but in total, China has significantly shot up the list. Again, this is through 2020, so it's pretty recent data. You can think of India, they will definitely be spiking in the next few decades. China will continue to go up. The United States has begun to slowly go down in terms of total usage, but per person, we are still the most significant users of, or producers rather, or emitters of CO2 on a global scale. China, though, has, per person, has begun to go up, and you could eventually see this number surpass the United States. Remember, China has 1.3 billion people, and India as well. And here's the idea of the carbon cycle. Again, this is not for you to memorize this graphic. This is so that you understand that there are, when the arrows are pointing up or down, that's either a source up or a sink down. So like the hydrologic cycle, water, right? This is the carbon version. So this is carbon movement, weathering and erosion of material, and then human carbon transformation. So of course, the combustion. Here's another carbon cycle. Again, this is not for you to memorize these numbers, but this is to give you a sense of what is putting or inputting the most carbon into the atmosphere. Well, gas reserves, oil, coal. What's basically putting more carbon in? So basically storing it. And so we're talking about dissolving inorganic carbon into the ocean. What are some of the sources? So there are inputs and there are sinks, depending on where the arrow is pointing to. And again, there's an overall imbalance that's taking place. But again, the point is not for you to memorize this graphic, is to get a sense that there's an imbalance taking place. There's more carbon going into the atmosphere that's being taken out of it. And as a result, there's more carbon that can basically store or absorb more infrared radiation. Here's a breakdown of the uptake. So there is an uptake that is in the positive of 5.1 gigatons per year. So some emissions contribute positive, the oceans absorb some of it, the land takes up some of it, but the land also produces some of it. So when you add all these numbers, you get this number. Okay? So here's the equation: 9.4 emissions minus 2.5 ocean minus 3.4 land plus 1.6 equals this overall positive number. And remember, positive forcing, warming. That's the key takeaway there. Let's look at it from a positive feedback perspective. So you have CO2 and methane increase. And you get the wheel, so you have a temperature increase, there's more evaporation, increase in water vapor, more warming, more evaporation, more water vapor, temperature increase. Again, you remember, what positive feedback implies a reinforcing of the original forcing. So if warming was the original forcing, a positive feedback will make it warmer still. So it's a bit of a runaway process. Make sense? All right, that's it for the lesson. I hope if you have any questions, please ask. Make sure that you review the slides, download them, don't print them. And anyway, I hope you're doing well. If you have any questions, ask, and I look forward to interacting with you soon. Talk to you soon. Bye.